Hello and welcome to today's ACM Tech Talk. In these unprecedented times, we hope that you and your family are healthy and safe, and we're glad that you're able to join us today. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of nearly 100,000 computing professionals and students. My name is Michael Zeller, and I will be your moderator today. I'm the CEO of DynamAI, where I oversee all aspects of a fast-growing end-to-end AI solutions company. I'm also an ACM member and serve as Secretary and Treasurer on the Executive Committee of ACM SecDD, which is the premier international organization for data science. To learn more about my background, please check out the bio window on your screen. For those who may be unfamiliar with ACM or what it has to offer, here's a little bit more information. ACM offers educational and professional development resources that bolster skills and enhance the career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. That's really the link you want to remember, learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing information published by ACM, including communications of the ACM and Q magazines. My personal favorite, the access to the ACM Digital Library, the world's most comprehensive database of computing literature. International conferences that draw leading experts on a broad spectrum of computing topics. Support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, the updated ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Now, before we get started, I'd like to quickly mention a few housekeeping items shown in the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find some additional widgets and resources. If you're experiencing any problems with the slides or the audio, press F5 in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can simply close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during this talk, please type them into the Q&A box at any time and click the submit button. I'll organize the questions as Michael speaks, and he'll reserve time at the end of the presentation to address them. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. And of course, check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentations, you'll see a survey on your screen. Please take a minute to fill it out and help us improve your tech talks in the future. You may also open the link to the survey at any time from the resource window. In addition, you can use Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACMLearning. We'll be watching for your tweets. We'll also have a community discourse page to continue the discussion after this webcast, including questions we won't be able to get to during the Q&A session. Now, today's presentation is the decision-making side of machine learning, computational, inferential, and economic perspectives by Michael Irvin Jordan. It is my great pleasure to introduce our speaker today. Michael is the Pehong Chen Distinguished Professor in the Department of Electrical Engineering and Computer Science and the Department of Statistics at the University of California, Berkeley. His research interests bridge the computational, statistical, cognitive, and biological sciences. Professor Jordan is a member of the National Academy of Science and a member of the National Academy of Engineering. He has been named a Neyman Lecturer and a Medallion Lecturer by the Institute of Mathematical Statistics, and he has given a plenary lecture at the International Congress of Mathematicians. He received the IEEE John von Neumann Medal in 2020, the International Joint Conference on AI Research Excellence Award in 2016, the David E. Rumelhart Prize in 2015, and the ACM AAAI Allen Newell Award in 2009. Professor Jordan is also an ACM member and, of course, an ACM fellow. Now, with this, without further ado, please take it away, Michael. The stage is all yours.
All right. Thank you, Michael. It's my pleasure to be here for the historical record. In fact, if you're watching this later, this was given in the time of the first wave of the coronavirus. In fact, if you're watching this from the future, we'd all be very curious to learn how this turns out. So if you could go to the chat box and tell us, we're all very curious about that. All right, so I'm a machine learning researcher. I've been working in machine learning for mostly my whole career, going back 3 decades. I see machine learning as having 2 major sides to it: pattern recognition, where a lot of the focus has been recently, in decision making, where there has been focus, but certainly less, and I'm going to focus on the latter. So let me go ahead and start with a little bit of outline. I will give a bit of historical background, philosophy, comments, and so on, and then we're going to get into 4 different areas where decisions are highlighted, where decisions in machine learning interact with other related fields. So in terms of historical background, I see machine learning as fundamentally a new engineering discipline. Okay, so before machine learning, there was computing, there was statistics, and the concepts that we use in machine learning are those developed in those fields and allied fields like optimization, applied mathematics, and so on, control theory. But what those fields didn't aim to do is to build planetary scale systems that do machine learning, that take in data, have human preferences involved, make predictions, and link it all up in large scale systems. So that's the perspective I take, which is that's an engineering discipline which is emerging, just like chemical engineering emerged from chemistry and quantum physics. A large-scale enterprise developed new concepts at thermodynamic scales that were much larger, and so on. So we're doing the same thing with this field of machine learning. So this is a pretty different perspective than the AI perspective, where machine learning just aids in the process of developing intelligence in the computer. That's a perfectly fine perspective. It's just not my perspective. I see it as less about individual intelligence in the AI sense and more about large-scale IoT-style systems that share data and make inferences and decisions. All right, so to support this point of view, if you go to the real world and you look at the real applications, just like a chemical engineer probably went to the real world and saw factories being built, I would offer the following. So already in the 1990s, there was large-scale machine learning. There was a first generation in the back end where companies like Amazon.com and others developed fraud detection, search, and particularly supply chain management systems. This was the origins of the cloud. There's a large-scale compute being used with large-scale data and machine learning algorithms. In particular, it was random forest back in that day to monitor and manage all aspects of supply chain. How long does it take to take a boat across the Indian Ocean, and so on. So they did that well so that Amazon could become a thing. And till to this day, there are hundreds of people in companies like that doing all of the back-end machine learning meet systems. So very much an engineering field. I think the next wave of activity in industry was to note that a lot of the data was not just about supply chains, it was about human beings, their preferences, their purchases, their transactions, and their in some sense, their desires, their utilities. So taking that data and bringing it forward led to recommendation systems and then to commerce and to social media. I think this is a second wave. I think it's a billion-dollar industry as well. It was not talked about nearly as much, certainly in the newspapers back in the day, but it was a major event, sequence of events. All right, come forward to today. I view the current era as focused on pattern recognition. So large amounts of data are being used to predict and to find patterns in data. So useful applications include speech recognition, computer vision, and translation. Those are human activities. So this starts to look more like classical AI, and it was eventually called AI, but it's really just part of the machine learning spirit of taking in large amounts of data, large amounts of compute, and using it for particular real-world industrial applications. I've yet to see the billion-dollar industry emerge here in this third generation, but certainly it's coming. I just want to emphasize by contrast, the first two really did happen, and they really had a major and less talked about impact. All right, and so what's next? So what I think is next is already actually happening. I would call this the era of markets. So it's not just one agent making a sequence of decisions or a decision in the classical AI sense, but it's a huge interconnected, let's call it planetary scale web of data agents and decisions. So think about the current coronavirus outbreak. It's a medical web of data, decisions, and inferences that are being made on the planet right now. And in an ad hoc sense, behind all of that is machine learning mixed with humans trying to respond to this outbreak. But you can think about commerce systems or transportation systems and more general medical systems very similarly. And I think fast forward a couple of decades, we will have kind of an engineering discipline that devotes itself to design, analysis, and diagnostics for systems like this. And I don't think we actually have that engineering discipline yet. We are building these things in very, very ad hoc ways, not just the coronavirus, but transportation and commerce and so on. So there are lots of new challenges emerging here. So let's dig into this a little bit, why intellectually this is true, not just as a matter of my opinions about reason and when I read the newspaper. So let's think about decision making, right? So you would be forgiven to think that a decision was just a thresholded output of a neural network in the current era, okay? But it's not really, I believe, adequate. So imagine you go into the doctor in a couple of years, and the doctor measures lots of things about your body, your height, your weight, your blood pressure, but also measures your genome, does a quick sequencing. And at the end of the day, there's a 50,000 dimensional feature vector describing you, which is input into a big pattern recognition system. And imagine that system has been trained with all the world's medical knowledge. So it's a big neural network, and it's been trained really, really well. So it can make lots of predictions. All right. And suppose that the output of one of those is a prediction that you're going to have a heart attack. And the threshold is set because of historical reasons at 0.7, and your number is 0.701. All right. So is that a decision that you all will have with high probability a heart attack? Are you going to take it as a decision? Well, absolutely not. You're going to treat it as an entree to a dialogue. You're going to say, well, wait a minute. What are the error bars on that, first of all? And those error bars reflect what kinds of uncertainty, what kind of data was gathered. Is it about people like me, or is it about a different kind of people? Is it about the same machine that's being used to measure things about me, or maybe an older machine? What if I were to exercise more? What if you would get a second opinion? We're going to want to run what if, effectively causal inference kind of experiments around that decision. We will change the data and see what happens. We will have a whole dialogue between me and, in some sense, the doctor. And then we make a decision, which is to wait and see, and so on. All right, so that's just one decision, but it's a consequential decision. It's life or death. It's an operation or not. All right, and so there will be issues of provenance, relevance, and dialogue issues that come up when you make really real-world decisions, including whether a self-driving car is going to turn left or right. That can be a consequential decision. Now, that's just barely scratching the surface, because decisions never occur in isolation. Even for me today, I'm not going to make one big decision. I'll make bags of decisions. I'd like the error probabilities over the entire bag to be controlled. Okay, I'd like the interactions to be taken into account. All right. Moreover, it's not just me; it's other people making decisions too. And just like with the coronavirus, these decisions are linked. If something works well for me today, that should be part of the network to know it should be tried for you tomorrow. All right, but it's not just that. In fact, it's over time, and it's all asynchronous, and it starts to get to be planetary scale. And so the way we measure accuracy here is not just with mean square error or type 1 or type 2 error. It's some kind of aggregate notion of error over time as it evolves, and it's all under control in some sense. All right, but now that's also still scratching the surface, because we're kind of back in the AI mode of thinking of each decision as somehow individually isolatable as having been a good or a bad decision. But in the real world, there's always scarcity and there's always competition. Of course, there's vast amounts of uncertainty too. And my allusion to the world's best neural network that knows all medical knowledge is of course fanciful, that in any given moment, the knowledge really is incomplete and it will change. But when there's scarcity and competition, moreover, there's not an obvious best answer. It depends. It depends on the context of the other agents around me, what they want, and so on and so forth. So there needs to be an economic perspective, bringing market kinds of ideas together with machine learning kinds of ideas. All right, so this is not a new notion that market should be part of computer science. It's just not really been the focus ever, especially when you think about machine learning. All right. So markets can be viewed as decentralized algorithms. They accomplish complex tasks. They are intelligent by any definition, really, as intelligent as our current computers. They are adaptive, they're robust, they're scalable, and they can have a very long lifetime. You don't have to kind of update the software every few years. All right. So that kind of the principles there that are essentially those of microeconomics need to be brought more into contact with machine learning ideas. Much of the work in microeconomics and in microeconomics applied to computer science didn't have data in mind. It didn't have inference in mind. It didn't have machine learning in mind. So that's what's going to be new here, is that we want to do this at large scale, and we don't know most of the preferences and all the other things that were treated as input to classical microeconomics. So there are going to be huge opportunities here. Moreover, the market principles, the microeconomic principles, mechanism design principles, were developed for previous eras. There will be new ones needed. New whole kinds of market principles will be needed. Okay, to make this even more concrete, let's. This is kind of where I got started thinking about this a few years ago. Consider a classical recommendation system. You all know what it is. It's a machine learning system. It keeps track of purchases and recommends items to one user if a similar user has purchased those items in the past. Okay, doing this at large scale, worried about the whole tail and the different kinds of items and users is really hard, and it's an ongoing research issue. All right. Nonetheless, it's become a commodity. You can download software, whole systems that'll do recommendation systems. And so people build business models trying this out in all sorts of new domains, not just books and movies. And problems arise. And I think people don't think ahead and realize that these problems are kind of obvious. All right. So let's just think about recommending movies, classical Amazon style recommendation or Netflix. So what if you recommend, the same movie to everyone or to many, many people? Well, of course, you're going to do this because the recommendation system is not trying to link up people directly. If I come in the morning and a certain movie is recommended and you come in the afternoon, it's going to recommend quite possibly the same movie to you. There's no constraint there. There's no load balancing, if you will. And is that a problem? Well, no, because there's no scarcity. You can copy the bits as many times as you want. All right. Similarly, with books, you can copy the book really quickly nowadays, print on demand. So scarcity doesn't rear its head there. Right. But if you go out in the real world and you become more of an economist, scarcity will obviously raise its head again and again. So if I build a really good restaurant recommendation system of the kind where I walk into a city, I pull out my cell phone, I push a button saying, I'm ready to eat, geolocate me, know some things about my tastes, about my price point, and so on, broadcast that to the restaurants around me. All right. They are on the other side of a market. They look at me and 10,000 other possible clients, and they have their preferences back on us. And there's some kind of a matching done. And then on my cell phone, beep, I get a bid from a nearby restaurant, and I look at it and maybe accept or reject. All right. So that's a very different way of thinking about a system. Suddenly I went way beyond recommendation systems and I went into a two-way market. If you do that, you can handle this load balancing problem. You're not going to make the same bid to the same person, to many people, and sell the same seat many, many times. But a classical recommendation system would absolutely do that. It would recommend the same restaurant to huge numbers of people if everyone in the city is using the system, and you'll have congestion. And you don't want to just solve that by randomly throwing some people in and some people out. Similarly, with recommending streets to drivers, you can create congestion, and you don't want to solve it by just you get to decide who goes down what street. You want to have them express preferences about how much of a hurry they are in today, what other options they might do on their trip, and so on and so forth. And there should be avatars kind of running an auction of some sense between street segments and drivers. Recommending stock purchases to people, you don't want to recommend the same stock to everyone. That's going to destabilize the market. So whole new issues come in when we start thinking about this. All right, so the alternative, as I've already alluded to, is not just create a whole bunch of semi-coupled recommendation systems, but create a market that blends recommendation system ideas with market matching ideas. So diners on one side, restaurants on the other, and both of them have a recommendation system looking at the other. All right. So this is not just let's do classical microeconomics and we're done. This is classical microeconomics assumed you knew all the preferences. Well, if I go to Shanghai and I'm looking for a restaurant tonight, I don't know any of the restaurants. I have no preferences, no clear ones, at least for the specific restaurants. I just have some history. And that's fodder for a recommendation system interacting with the matching system. And of course, we're doing this in the context of other people who've been to Shanghai that may or may not be like me. So I hope you see there's a whole rich thing emerging here, emerging market ideas with machine learning ideas. Let me give another example, which is very much real world and important to me personally. So music, the more people are making music than ever before, and they're placing it on sites like SoundCloud. It's being streamed to people, and more people are listening to it than ever before. So you would think there's a flourishing market for music, and people are making money, and it's a wonderful success of computer science. And you would be wrong, because no one's making money on music. The people making it are surely not. If you look at the data, about 95% of the songs being listened to today were songs written in the last 2 years and written by people you never heard of, maybe 16-year-olds who just did it on the weekend or for fun. All right, that's maybe a surprise to most of you, but if you think about just people living in inner cities for whom Latin music or hip-hop music is the way of life, they're listening to it all day long. They're not listening to the famous musicians. They're listening to the cool latest stuff, all right? Yeah, so you think the people making that music, the cool latest stuff, are making money, but they're not making money, okay? So how do you fix this? The problem here is that IT has kind of stripped away the economic side of this. They've just taken the bits and streamed them everywhere and made it possible very easily for people to listen. That's great, but you've lost all the economic value. And people try to restore economic value by selling subscriptions or doing advertising like Spotify. But that's now not a real market. That's not between the producers and the consumers directly. That's an artificial side market. And they're not giving money back to the musicians, at least not very much. All right, so how do you fix this? Well, it's really not that hard. You directly connect the producers and consumers, you being the computer scientist building platforms, right? So you provide a dashboard to the musicians. They get to see every week, at the end of the week, a dot on a map where their song has been listened to. And maybe they discovered that 20,000 people listened to their songs in Dayton, Ohio last week. They can show that to the venue owners in Dayton. The Dayton venue owners are excited. There's a popular person. They bring them there. They give a show and make $20,000. And that continues 3 or 4 times during the year. That person now has a job. They have a career. And they can now manage that career and learn more about it and make other kinds of offers. Once they know that someone's listening to their music, they can make offers to come play at a wedding for $10,000 and so on and so forth. So advertising is not needed here at all. IT can create a market without trying to think about advertising as the way to monetize it. Okay. Now, it's not just music. You can do this for many other domains, but I do want to emphasize that this is already happening. There's a company called United Masters. I'm on the board of this, but I want to recognize Steve Stout, whose picture is on the screen there, a really brilliant entrepreneur who's heavily involved in the IT world, but also, mostly in the music world, and has created a company which has signed up, I think, over 200,000 musicians now who are seeing this dashboard and allowed to produce their songs. And their music is being heard in places like the NBA website now and many other places. So this kind of thing is emerging, and it's using machine learning, data science, and the back end to support the creation of a new market. So the social consequence of this is you can create new jobs. Once you have flows of data and they're valuable, if you reify those and make them available to 2 sides of a market, and then a market will emerge. And AI in this sense can be a job creator, not a job killer. You're not trying to replace humans, you're trying to empower them to do new kinds of things. It's not just music, it's other forms of entertainment. It's artists who may want to paint things for people's homes. So it's something like a gig economy, but done in a more sound microeconomic sense, or a more thoroughgoing, shall we say, microeconomic sense. Okay, so that's kind of an introduction. So let me turn now to research. I've been thinking about these kind of things for 5 to 10 years and have been working on it with students and have a lot of projects. And I'm going to tell you about a few snapshots that highlight a few of the issues that arise and initial attempts to solve them, and just kind of highlight the thinking style. So here is just some of the problems that you can start to think about even more broadly. Multi-way markets in which agents have to explore to learn their preferences. They don't know them a priori. And multi-way markets in which they see other sides of the market via recommendation systems, and so on and so forth. So we want new principles, somewhat like a chemical engineer who wanted new principles to build these healthy learning-based markets that are stabilized over long stretches of time. Okay, so here's a particular project I want to start with, where we brought together an idea from learning, the Bandit idea, and an idea from microeconomics, matching markets, and saw what happened when we put the 2 together. So recognize Lydia Liu and Horia Mania, who are students with me at Berkeley, And we have a paper on this that was due to appear in this summer's AI Stats meeting, which I just learned this morning is being canceled or postponed, not canceled, postponed. Okay, so my favorite idea in machine learning is called the multi-arm bandit problem. I like this even more than supervised learning and neural nets because it's really learning. It's not just mimicking data that came from somebody else. So the agent has a number of options, in this case 3, and they don't know which one's best. Each one of them gives them a different reward distribution. So they have to sample them. They have to pull each arm a few times and see which one seems to be best. They explore. But they want to eventually pick the one that is giving them the highest reward so they can exploit. And this trade-off of exploration and exploitation is what's studied in the Bandit literature. And mathematical relationships are found. Typically, you want the regret, the amount of exploitation you get, the reward you get over time relative to an omniscient expert which knew a priori which arm was best. You want that regret to scale as, let's say, logarithmic in the number of rounds you play. If it scales as linear, that's bad. You're not learning anything. Logarithmic is the goal. So you pick an arm, and you get a reward back, and maybe you'll now pick that arm again if the reward is high. Maybe you'll pick some other arm to explore a little bit, and so on. So the algorithms that are developed for that, there are a range of them. The most famous one, arguably, is the upper confidence bound algorithm. It encapsulates in one idea both exploration and exploitation. So on the right there, I've shown little error bars on the rewards. So for the first arm, it looks like you're getting a pretty high reward, and you have a pretty tight confidence bound. It's looking like a pretty good arm. So should you just pick it all the time? Well, no, arm 2 here, looks like it has a lower mean reward, but has a high uncertainty because you haven't picked that arm very much. So instead of picking the highest mean reward, the one in the middle, you pick the highest end of the confidence interval, the high upper confidence bound. And in this case, arm 2 has the higher upper confidence bound, and you'll pick it not because it looks like it's the best arm, but because it's unexplored. And if you pick it a few times, presume that confidence bound will narrow, and you'll learn it's not such a good arm after all, and you'll start to pick arm 1, but you don't know that currently. So this algorithm is guaranteed to have a logarithmic regret under certain assumptions, and it's a plausible, interesting algorithm that was developed in this literature and could be applied in many other literatures. Okay, so again, you pick arms and you adjust the confidence bounds. In this case, the upper confidence bound is arm 2, so you pick it. Okay, I don't know why that's happening. All right. Idea number 2 from the microeconomics literature. Let's take matching markets. All right, so here we have 2 sides of a market. We have buyers on one side, sellers on the other. They both have preferences for the other side of the market. Those preferences are assumed known a priori and well specified by both the buyers and the sellers. So kidney markets are a famous example where a Nobel Prize was given, but there are many other matching markets, interns in hospitals and so on. You all probably know about this. So if you know all the preferences a priori, you can run an algorithm. Gale-Shapley is a famous one, where you iteratively update the matching, and you converge towards a matching which is stable, has nice microeconomic properties. All right, so that algorithm is the Gale-Shapley algorithm. You iteratively make proposals to the other side. Okay, so what if we put these 2 ideas together? We can have matching markets meeting bandit learning. All right. Well, why would you do this? Well, if the participants in the market don't know their preferences a priori, but they can only observe noisy utilities by repeated interactions, then you have a bandit problem, but we're going to have a bandit problem where there are multiple participants. Okay, so we have a human and a bear. They're both playing the game. All right, so if they pick the same arm, we're going to have a rule now, which is that only one of them is going to get a reward. All right, so that we brought in scarcity into the problem now. All right, which one of them gets it? Well, the other side of the market, in this case, the arms, are agents too, and they have preferences back on the agents. So they, arm 2 may prefer the bear, and I, as the human, are going to be out of luck. I'm going to get a 0 reward. Now, if I observe that happening a few times, that I like arm 2, but the bear seems to like arm 2, and the bear seems to win, then I might back off hedging my bets and picking the other arms more than I otherwise would have done. So I will have a penalty to pay for that because the bear is involved, but that's just life, right? And I want to quantify how much I'm going to lose by that property. We have different reward distributions of the different arms in our setup, so it might be that both of us are going to be perfectly happy, but we don't know that a priori. Okay, so here's our version of a bandit market. Agents on one side, arms on the other. They have preferences on both sides, but they're both unknown, and they learn as via Bandit-style algorithms as they go forward. Okay, so here is a particular algorithm that we've defined. Actually, before I get to the algorithm, let's talk about our notion of regret. I don't want to get into all the details here, but the regret notion is, what if I knew my preferences a priori and I handed them to the Gale-Shapley algorithm and it ran and did a matching? How bad am I relative to that? That's going to be my notion of regret. Okay, so our algorithm is specified here. We call it the Gale-Shapley upper confidence bound. It's kind of obvious. All right, so the agents are going to use upper confidence bound technology to update their reward distributions on the arms. Okay, they don't submit the mean reward. They submit these rankings, these upper confidence bounds, to a matching platform. That platform uses Gale-Shapley on the upper confidence bounds and returns a matching. Okay, that allows me to be allocated an arm, and then I get a reward, and I update my upper confidence bound. Okay, so that's a particular algorithm. It's a centralized algorithm. We're also working on decentralized ones, but this is one that we've analyzed in our first paper. And our analysis shows that, in fact, you get a logarithmic regret for this. So this is good. This is that the system really does learn. In the denominator is a term which is a reward gap that depends on the presence of the other agents, and we can quantify that term. It's generally bad. It raises the regret, but still the regret is logarithmic in the number of rounds. So you pay a cost, but it's not an endemic cost, if you will. Okay, that was one little snippet. Let me give you a second one. Now that you know more about UCB, you will want to use the UCB in many other places. A lot of machine learning doesn't have notions of uncertainty, and it doesn't have error bars. So it tries to update the mean or to make the mean square error small and so on. We want to bring UCB and decision-oriented ideas, uncertainties, into contact with other areas of machine learning. All right, so here's a project where we've done this with reinforcement learning. We're now going to be looking at sequences of decisions. Okay, before we were looking at one decision at a time, just when there was scarcity. That's one axis. Here's another axis. What if we have sequences? So this is work with Qi Zhen, Zheyan Alan Xu, and Sebastian Bubeck. This will be brief. I don't want to introduce reinforcement learning. I think many in the audience will know about it. We have a Markov decision process where there's a state. I make an action, and that gives me a reward. So it's an action. It's like the Bandit problem, where we additionally have Markovian state. Okay, and the reward will be the cumulative reward over the rounds here. So you can define a regret notion. It's usually not done in reinforcement learning, but it's also natural to have a regret notion here. And the applications have been, often to game kind of problems, but there's many industry problems that have this flavor. And there's been a debate for a long, long time, as long as I've been in the field, really, about model-based versus model-free approaches to reinforcement learning. Should you try to model the transition model, the state transitions, and then based on that run an algorithm that takes that into account, more like a classical operations research kind of model or control theoretic model? Or should you somehow try to find a policy directly, that's called model-free learning, by in some sense doing a gradient method in the space of policies and trying to find out what works? A little bit more like a Bandit algorithm, okay? So I'm not going to resolve this debate, but I want to contribute to it. This slide is too small and too busy. I just want to say, if you know what Q-learning is, it's a dynamic programming style algorithm that updates a reward distribution given the state or an expectation of a reward given the state and given an action. All right. This version right here, which I apologize for being small, is called a greedy version, where you either take the maximum Q value with some probability, high probability, or you randomly explore some other action with a small probability. It's called epsilon greedy. This is what's often done in practice. It's an ad hoc method. And our paper proves that it's actually quite a poor method. This is not what you want to be doing for Q-learning. This thing has a terrible regret. There's a better algorithm. Again, apologies here. I don't want to get into details. But if you'll see the little red piece there in line 2, that's the upper confidence bound. You're not taking the mean Q value. You're taking that plus an upper confidence bound, and you're using that to make a decision about your next action. So all we've done is taken UCB and pulled it into Q-learning. And now we prove a regret bound here. And this regret bound, again, a little too small here. I'm going to show you a summary slide on the next slide. Turns out to be square root of the number of rounds. So there's a bunch of other stuff there, but the important part is the square root of capital T. That is the regret of this UCB version of Q-learning. Okay, so on this slide, this is in our paper. The top 5 lines are all model-based results. This is the theory of Q-learning, so or reinforcement learning. So those are analyses which show that you get a square root of t regret for the model-based methods, right? The next 2 lines are model-free analyses before ours, and you were not getting a square root of t regret. You were getting a linear regret or slightly sublinear, right? This new analysis shows that Q-learning with UCB, on the other hand, gives you a square root of t regret. So commensurate with the model-based. So this says, in some sense, surprisingly, in a well-posed theoretical sense, model-based and model-free are equally good. Of course, that's not the whole end of the story. There's other constants and parameters, but that is it's important to think that when you bring decision-making principles in, the bound goes down. And how far does it go down? Well, it goes down quite far. All right. If I were in a normal talk, I would pause for a moment. I'm going to pause here, just take a breath, let you absorb kind of what I've been talking about. We've got 2 more segments to go. And all of these are also papers available that if you want to follow them up, you can. So it'll be somewhat brief. But this is a third axis in the decision-making space. So far we've done bandits, which are one decision at a time, but we brought in economics ideas. We had scarcity, okay? The second one was we had not just one decision, we had a sequence of decisions. So we're doing reinforcement learning. Now we're going to do multiple decisions, but it's bags of decisions. And it could be within a single agent, or it could be across a set of agents. But the key is that we're going to do bags of decisions, and we're not interested in just the accuracy of a single decision. We're interested in the accuracy aggregated over the entire bag of decisions. So this brings in the idea, a very important idea in statistics called the false discovery rate. And we're going to be doing this in an online setting where we want to control our overall aggregate error over a bag of decisions, but we want to do it at any time as we're making decisions. So Aditya Ramdas and Tiana Zernich have worked with me, colleagues at Berkeley, on this project. And I want to recognize Foster and Stein had a paper at Pennsylvania, at UPenn, that kind of got this anytime or online control started. And then Haranori and Rosette and Javan Martin and Montanari have made major contributions. Okay, so what is the statistical problem now? We've talked about things that are not so statistical. This is going to be very statistical. Multiple decisions. So hopefully some of you have seen this little cartoon where if you're doing hypothesis testing or trying to make a decision under uncertainty, you have to think about the error rates, and they might be false positives, they might be false negatives, and you want to control those. So here in this little cartoon, someone runs in and says, hey, I have a hypothesis, which is that jelly beans cause acne. And someone says, scientists investigate. All right. So this could be, a hypothesis that ibuprofen makes you sick when you have, COVID-19. So it sounds interesting. It sounds kind of crazy, though. Maybe it's right. Maybe it's wrong. We got to collect some data. So here they do a randomized controlled experiment, perhaps, and they put, 50 people into the jelly beans condition and 50 people no jelly beans. Afterwards, they find that the acne distribution is kind of randomly distributed between the two. They're able to quantify that with, say, a permutation test and get a p-value bigger than 0.05. So they say, no association there. That was a nice idea, but it didn't work out. Right? But it never ends there in real life. The person comes back and says, well, I heard it's actually blue jelly beans or green jelly beans that cause it, or red. So people start running lots and lots of experiments. Now, every experiment, they are good statisticians. They get a new, fresh bunch of people. They run a new randomized controlled experiment, right? But I think you all know what will happen here. At some point, randomly, by chance alone, the 50 people they put into the jelly beans condition already have bad skin. And the 50 people they put in the no jelly beans don't have bad skin. And then after 6 months go by, they look at them and they say, oh my God, the jelly beans people have bad skin. That must have caused it. All right. And so it turns out that there's a p-value less than 0.05. They report that in the journal because now they can get a publication. And the newspapers are scanning the journals for all the cool new latest ideas. And they say, well, this is surprising. Someone discovered that green jelly beans cause that. And they publish it. And we've just made it a noise amplification system. And again, the current situation with COVID is one of many examples where this is happening and will continue to happen. You don't want this to happen. All right, so statisticians have been aware of and have tried to solve this problem and have made a lot of progress ever since the mid-1990s when Benjamin and Hochberg defined the false discovery rate. Let me define that now for you. We're now looking at not just one decision, we're looking at a set of decisions. So we're gonna make 9 decisions here. And in statistical language, 5 of them are ones where you should not make a discovery. You should say, nothing's happening there. No, the jelly beans don't cause acne or whatever. So that's P1, P7, 4, 9, and 8 on the left, the gray ones. Whereas in 4 of the cases, there's actually something to discover. And you'd like to make a discovery in those cases and not in the others. So suppose you run some algorithm, maybe some neural net or something that makes a decision, and you make discoveries in these 4 cases. So you discovered 2 of the non-nulls, that's good, but you discovered 2 true nulls. Those are false positives. All right. Now the false discovery idea is that you don't look at the false positive rate, i.e., among the true nulls, how many times did I make a mistake, or the sensitivity among the non-nulls, how many times did I make a discovery. Okay. You look at a different notion, which is of the discoveries I made, how many of them were non-nulls, where I should have made a discovery, or how many times did I make a discovery which was a true null. That's a false discovery. And the false discovery proportion is just a fraction of false discoveries over the total number of discoveries. So in this case, it would be 2 over 4. That's not too good. That's 1/2. All right. And the false discovery rate is just the expectation of this over multiple experiments. It's the thing you can do the theory about because you're taking an expectation. It's a frequentist quantity. Okay. So that's the FDR, expectation of the FDP. Okay. So here is a slide which hopefully you will remember. This is important. So let's suppose we're in some company, say Amazon, say Google, whatever, we're doing 10,000 A/B tests today. That cost us some money. We got to run these experiments, but we have the money. And what are these A/B tests? Well, it could be like we have our website and we want to decide, should the background be blue or green? Or should we have the widgets certain size or whatever? And you hopefully know that companies like that do run 10,000 A/B tests a day or more. And their whole website has been designed with these A/B tests, making decisions all along the way. So this is very common. Now, let's suppose that 9,900 of these are actually true nulls. There's nothing to discover. If I change the website from blue to green, I don't get more people coming. All right? This is typical in a mature industry or a mature science. There's not much left to discover. All the easy things have already been done, and most of the things you try now aren't real. Then let's suppose, and indeed, the only real ones, there's only 100 things to discover out of this 10,000. But you want to discover those. That's the whole goal. So let's suppose you build a neural net or some system that's really, really highly accurate in the classical sensitivity, specificity, or precision recall sense. So maybe the type 1 error rate, the 1 minus the specificity, is really good, 0.05. So of the times when it's really, truly null, you say null 95% of the time. So of those 9,900, you're going to only say, I made a discovery 495 times. So the fraction is really good, 495 over 9,900. It's 0.05. All right, similarly, this neural net has a good type 2 error rate or power, meaning that when it's non-null, where you should make a discovery, it makes a discovery 80% of the time. All right, so this is a pretty good accuracy by the usual criteria. And in fact, of those 100 non-nulls, 80 of them are discovered. So I have 80 true discoveries. Right, but here's the problem. Your boss doesn't care about sensitivity and specificity at all. Well, maybe a little bit, but they really don't care. What they want is they say at the end of the day, I gave you $1 million to run 10,000 A/B tests today. Show me the discoveries you made. I don't care about the non-discoveries. I'm not going to act on those. But the discoveries, we may change the website. We may spend more money. We may really invest. It'll cost us more money. How many discoveries did you make today? And you say, well, I made 575 discoveries. And the boss says, great, let's act on them. The problem is that 495 of those are actually false, okay? Over 80% of your discoveries are actually false. And the boss will learn that because they will implement them and spend a lot more money, and they will fail, and then you will get fired, all right? So I hope the message here is that false discovery rates can be huge, can be very, very high, even though the type 1, type 2, or sensitivity, specificity, power, precision recall, all those concepts are actually well under control. Okay, so again, statisticians have known this for a while, and they have developed procedures which control the FDP, or its expectation, the FDR. All right? And I'm not going to get into those procedures, but I'm going to tell you that in the last 5 years or so, perspective, which has emerged, which is combining this with online ideas, online learning, if you will. All right, so now I don't want to just wait to the end of the day and say how many discoveries have you made and what fraction are good and do this in one big batch. I want to have you be doing this for years, and I want to be your boss and just come into your office anytime and stop you and say, how many discoveries have you made up until now? And you say 80. And I say, how many of them are false discoveries? And you say less than 5%. Then I come in a week later and I ask the same question. Now you've made 125 discoveries. And I say, what fraction are false? You say, guaranteed you, less than 5%. And I want to be able to do that at any time in your life. Is that possible? All right, and the answer is that it is possible. Okay, it's somewhat surprising. You would think in statistical sense that if you keep having a fraction, a threshold, and if you make that threshold a constant, by the union bound, the probability of making error just goes up and up and up. And eventually you have to stop making the tests. You're run out of wealth, if you will, alpha wealth. All right, but the FDP is a ratio, and you can make that ratio small in two ways. Either by making the numerator small, the false positive rate small, but eventually that you can't do, or making the denominator big, making more discoveries. All right, so in fact, there is an algorithm that every time you make a discovery, it gives you a little wealth, and then that wealth decays. And then you make another discovery, it gives you a little wealth back and decay. And that algorithm is this online FDR control. So if you want to follow up on this, you can go to my website and get a start. But again, some of the other authors I alluded to on that first page have papers as well that I want you to consult. All right. So, so the last part of my talk will be about trying to put all this on a platform. So I'm a big believer in eventually taking ideas and making an engineering field out of it by building a platform which tries to do these things in some generality. So I'm going to talk about a project with a whole raft of colleagues at the RISE Lab in Berkeley. Philip Moritz and Robert Nishihara most notably have led this, and Jan Stojka, my faculty colleague here. This is a project called Ray. It's a distributed platform which is focused on the decision-making side of machine learning. It can do the pattern recognition side too, but it usually does that just by bringing in TensorFlow or PyTorch. But it builds all the other stuff around that allows you to make heterogeneous decision-making in real-time environments. And I want to tell you about the principles that we're using to build that. All right, so one way to look at Ray is that it's a platform that allows you to do distributed computing, especially learning computing, with a touch of a button. Okay, you can run it on your laptop or you can run it on 10,000 processors, and you don't have to change hardly anything. So the current ecosystem doesn't have that property. People have developed distributed training, distributed model serving, streaming, and so on. And each one of them is a separate whole distributed implementation of an underlying algorithm. Okay, so there's distributed training algorithms, distributed model serving, distributed streaming, and so on and so forth. So at some point, you'd like to unify these things. You'd like to build a single distributed system that handles the 10,000 processors, handles the communication, handles the data structures, and these capabilities are to build as libraries on top of this system. All right, so that's one way of thinking what Ray is doing. It's building a single layer that handles the distributed part of distributed machine learning, especially in the decision-making context. Here's another way to think about what Ray aims to do, which is if you think about what a modern computing language such as Python provides, it's functional programming and it's object-oriented programming. When I started, I learned to program in C, which had neither, and then I watched the debates rage over the years about whether functional programming or object-oriented was best, and Python and other languages sort of showed us in the end that you need both. They both kind of win out. All right, now when people went to very highly distributed systems, a la MapReduce, they did not use Python. They built their own language, and that language was a functional programming language. So MapReduce, those are functional primitives. They threw away the state because it was hard to do at that kind of scale. So Hadoop, Spark, and so on are functional programming, basically. What Ray aims to do is to restore functions and objects in a distributed context. So it provides distributed functions, we call those tasks, and using classical programming language nomenclature, we call distributed objects actors. All right, and so Ray does a lot of work behind the scenes to make tasks and actors seamlessly work across either one laptop or 10,000 or whatever, however many at any scale that you want to work at, okay? So indeed, we're replacing the classical system with another layer which has tasks and actors in it. And underlying that is a whole machinery involving dynamic task graphs, which I'm not going to be able to get into. But just to say that this is, so 3 years of development have gone into this in the open source environment. Just briefly on an API here, it's a very stripped down API. Here's a little bit of Python that's just defining a dot product between vectors. If we want to make this run on not just one processor, but on as not many processors you want, you add a decorator, ray.remote, that says run it on the cloud. And then when you actually make the calls, you use the remote versions of the functions, and ray.get at the bottom there actually returns the results. So there was a lazy evaluation that ray.get actually makes happen. Similarly with objects, here's a classical counter object, which has state now. We add a decorator to say I want to run it in the distributed setting. And then when you call it, you use the remote versions and use ray.get. All right, so behind the scenes to do these things, there is a lot of scheduling going on, and there's a lot of object control going on. You cannot see the details on this slide. I just want to say this is a piece of Python code which does hyperparameter search for neural nets. It's the single-threaded version, and one's on one laptop. And this is not a good situation where single threading it makes sense. If you try out one hyperparameter, you kind of want to learn pretty quickly that's a bad choice and move on to something else. So you want to do this in a distributed setting, do that in parallel, but it's not MapReduce style parallelism. You don't want to have synchronous waiting between the different processors trying the different values of hyperparameters. If one of them is bad, you want to quickly learn that and have the processor do something different quickly. So you want a dynamic task graph. You don't want a block synchronous model. So here is the code that someone wrote for single parameter hypersearch to turn this into Ray code to let it run on in parallel. The only changes were those red lines right there. So there's like 5 or 6 places where changes were needed, where decorators were added to just, it's still Python, it's just a little bit of a change, all right? So we have libraries, and there is a working system. There's now actually a company called AnyScale, which is making this industrial strength, but still open source. And here are some of the architectures, some of the algorithms, and some of the multi-agent kind of capabilities that are currently available on top of Ray. The architecture, again, details can be found on our paper, but indeed it has object stores, object managers, and schedulers behind it. A lot of more work is being done behind Ray to make all this easy at the user level, but just to let you know that it is all sitting there. This is an older slide, but just to give you a flavor, this is performance. You can do 1 million tasks per second when you're up to 60 nodes, at least in this earlier version of Ray. So this is industrial strength. And here's an example in an actual real-world company. So you can see on the left the cell phone. So if you can see, there's actually Chinese characters there. This was Ant Financial, which runs the 11/11 Singles Day in China, where the shopping volume goes up by huge numbers of factors. So they have to update models during this whole process. They had their original legacy model, and they were updating it once per day at that scale. And when they spent quite a long time improving the model and got it down to from 1 day to 1 hour, and the click-through rate went up by 5%. They are working with Ray now as an open source project. It's the first company in China that I'm aware of that is doing open source development on a major project of this kind. You can see their code in the GitHub rep. And they re-implemented this using Ray, and the click-through rate went down to 5 minutes, from 1 hour to 5 minutes. So this is being used in production in that setting currently. All right, I'm about ready to finish. Just to say this is open source. Here is a GitHub repo. The downloads in 2019, we were seeing an exponential growth there. This is a kind of exponential curve I'm liking to see. There are other ones I'm not liking to see right this moment in history. Here are some of the industries which have bought onto doing Ray development and actually using Ray in various production environments. I don't have Amazon on there, but I want to note that Amazon is also currently engaged as well and making a bet on Ray. So in summary of that part of the talk, this is distributed Python, open source. Please try it out. You can have it on your laptop, or you can run on the cloud just as easy. And there's the OSDI paper that will give you the details. Okay, so I'm done. Popping back up to the very top level. Hopefully you found this interesting, and hopefully it expanded your appreciation of the range of machine learning. Machine learning is pattern recognition plus decision making at least. It's many other things too, but those are two big pieces. The pattern recognition has been the emphasis in recent years, and all the deep learning work that's mostly focused on that. I think that's great. That's major, major progress, but it does not solve the machine learning problem, especially if you define the machine learning problem not just to be classical AI, building a single agent, but you define it to building new kinds of networks that span human beings, multiple geographies, multiple time scales, for all kinds of modern tasks involving medicine, commerce, transportation, and so on. I wouldn't even necessarily call it machine learning at that point. It really is an emerging new engineering discipline akin to chemical engineering or electrical engineering emerging in the past. I think that's the right scale and scope to be thinking about what we're actually doing right now. All right, so with that, I'm now finished. I'd be happy to take any questions any might have. And again, recognizing our current historical juncture, all of you, stay safe, and we're connected worldwide. And I'm glad to at least have this hour with you. Thank you.
Excellent presentation. Thank you, Michael. This was very exciting, and I couldn't agree more that kind of the decision-making part is something that we have to move towards with machine learning. It's really, the ultimate business decision that you make that provides the value. And I also likewise enjoyed your focus on the platform at the end of the presentation, because the engineering challenges with implementing scalable machine learning systems and decision-making systems are often underestimated. And I think your traction and your downloads of an open source project show that there's a tremendous need in the market for such a solution. We have a little bit of extra time today, so stick around. Let's move on to the questions and answers session here. And maybe I'll start with a kind of a very high level formal question. One of the earlier questions, which might have become clearer along the presentation, was what is really the formal definition of markets? That was one of the early questions.
Right, good question. So first of all, I'm not a microeconomics person. In my career, I move into new disciplines, and I put textbooks, like undergraduate style textbooks, next to my bed, and I read them. And I did that with computational biology years ago, with physics years ago. I'm now doing that with econ. So if there are any econ sophisticated people in the audience, my due apologies for anything I said or I'm about to say. Just to say, my understanding and appreciation of the field is that markets are there's not one definition. There's a rich collection of ideas which have market kind of properties to them. One useful division is between matching markets and auction style or markets where there are prices. If I don't need money in the former. So if I'm trying to match people in a kidney market, a kidney exchange, I'm not trying to price that. I'm simply trying to find someone on one side of the market to match to someone on the other side of the market. And I have to have everyone express their utilities so that I can do a good matching that everyone's happy with. But given that, I don't have to set prices. The other kind of markets are often auction-based, where I do set prices. And maybe it's an auction, or maybe there's some other mechanism that ends up setting the prices. But I try to get people to express their utilities via price, where they eventually make a decision, buy or sell. Auctions are needed to do that. The price effectively conveys information to everybody in the market in a different way than we're used to thinking about information. And so those are two broad classes of markets. We've focused on the matching markets. They're a little easier to think about in some ways, but they're ultimately, I think, less powerful. You need prices, and you need, so the examples I gave, like in transportation, which path do I get to the airport today? Well, if everyone wants to get there quickly, you just can't send everyone down the same fastest path. So I've got to say, well, today I'm not in such a hurry. I'll save some money for a future day. And that notion of money, whatever that means by money, it could be points or credits, has got to be in there so that someone else who's in a bigger hurry today can spend their money, and we all are sort of happy over time. So prices serve a very important coordinating role there. So I'm not answering your question. I don't have a definition of markets, but they are sort of interacting. So the economics, the definition, I guess, is sort of the science of decision-making or scarcity. So, machine learning is somehow the science of decision-making under uncertainty, or really statistics is that. So if you put uncertainty together with scarcity, I think you start to get the scope of what we're talking about here.
Excellent. Yeah, I think we have a very large audience, so bear with me here. There's a lot of questions coming in. One that actually just popped up, which I thought might be a little bit related to this. If we're talking about markets and pricing. So the question here is, how does the idea of a connected system and decision-making in that system influence the topics of bias and fairness? Of course, that's a big, wide question, but bias and fairness always seem to be popping up.
Yeah, no, they're really important questions. And there's not going to be one definition of bias and one definition of fairness. There's going to be many kinds of definitions, and they're all going to be responsive to context. Fairness is somehow a balancing kind of thing, that everyone's treated the same in some sense, but that's way too narrow. I don't want to be treated the same as someone else who has different preferences from me. I want our preferences to be respected. So find out, to be fair is to actually assay people's preferences and give them things that are closer to what they want. At least that's part of the ingredient. So it can't be just that it's a balancing thing. Also, if you think about, if you're measuring how well people perform at a job for, trying to, assay whether she get a promotion or not. Well, if someone is, a pregnancy will make you somehow less able to do certain kind of things, you have to be, you're pregnant, you have to be lying in bed at some point. We would view that as completely unfair that such a measure was used to assay your ability to have a raise or to move forward in your career. So that's a normative decision. It's not a balancing. It's a balancing in some ethical sense. And so the measures I'm aware of in fairness and bias don't talk about things like that, but they have to eventually. But just conceptually, fairness and bias partly have an economic story. It's relative to what the options are, relative to the scarcity, relative to the other people around me, what's biased or what's fair. Okay, so if without having the economic ideas in there at all, I think we're just going to get stuck. We're going to stop short of trying to even attack those problems. But also think about just bias in a less normative sense. In an op-ed I wrote last year called Artificial Intelligence, the Revolution Hasn't Happened Yet, which you can find on the Harvard Data Science Review with commentary. Highly recommend the commentary. I mentioned a situation where provenance was an issue. It was a medical problem in my family. We'd had an ultrasound which looked problematic and almost led us to have an operation done. But we found out the data on which the inference had been built was 10 years out of date, and a new machine had come which changed the nature of how we interpreted that decision or that data. All right, and so there was a bias there. It was giving us an error rate which was wrong. It wasn't because the data was collected badly or because the statisticians didn't do a good job. All that was true. It was just stale data. So that's a database concept, really, that there should have been provenance. I should have known that there was stale data. I had to go look it up in the literature. But a good overall system would have the database people doing the provenance there, but it's not just classical database provenance. It's how relevant is some data in the past to the current decision I'm making. And relevance is a hard word to get your hands wrapped around. So that's also part of the bias and fairness thing, is that what data we're using and how relevant it is in a normative context. So this is going to take decades to work out, folks. We should be working on that right now, but we got to partner with legal people and social scientists and psychologists and range. It's all of society. It is this kind of grand scope of this new engineering discipline to partner with all these kind of other areas and to work these things through in different kinds of contexts.
Excellent. Okay, great. Another more technical question, I think, related to Ray. One of the questions was, can we use TensorFlow instead of Array? I think maybe if you can differentiate. Not instead of. Ray is much more flexible for doing decision making and asynchronous tree search, and it really is distributed Python. It can have TensorFlow inside of it, so TensorFlow can be one of the actors. All right, and that's what people are doing right now. They're running Ray, and TensorFlow is an actor. It has the state, needs state. So Ray absolutely is happy to work with TensorFlow or PyTorch as an actor. But TensorFlow or PyTorch do not aim at being the kind of distributed operating system or distributed programming environment language that Ray aims at being. Mm-hmm. Okay. One more technical question is related to the examples that you gave before on reinforcement learning. And does the path taken affect the reinforcement learning outcomes? Could there be a local minima or maxima that hangs up that entire learning process?
The path totally impacts the total reward. The way to think about reinforcement learning is it's just dynamic programming. And dynamic programming does find a global optimum, but at a huge cost. And so reinforcement learning is a stochastic Monte Carlo methodology for trying to do dynamic programming. Okay, and there are proofs that it will eventually converge, but the eventually is often an asymptotic or very, very long kind of proof. But as with most machine learning, we've just found that these local methods that are greedy, eventually start to have more guarantees that you might have thought, and will tend to work better in practice. That said, I'm not bullish on current reinforcement learning for industry. I don't think we're there yet. I do think that these, the complexity of finding these kind of dynamic programming style optima is way beyond what we're able to do now. You need simulators to do most of these things, and the simulators have got to be very accurate, and that's fine in games where there's little uncertainty. But as soon as you move to real world problems, you don't have the simulator, and you're kind of getting stuck. So this is, again, going to be a decade-long kind of project to get that style of decision-making going. Right. So, but anyway, that said, we've moved beyond just kind of local optimization when we're talking about reinforcement learning. We are aiming to do find the best policy overall.
Mm-hmm. Excellent. Okay. Maybe one last question here before we run out of time. One that I also find very, very intriguing is always, machine learning and AI is such an interdisciplinary field. And so one of the questions from the audience is that they're interested in what kind of engagement other experts from other fields really contribute to your research in machine learning.
So I tend to do too much definitions these days, and people sometimes get mad at me for that because they don't like my definition. But I will stand behind the one I made at the beginning of the talk, which is that I think of machine learning is to statistics and computer science and, let's say, control theory what chemical engineering was to chemistry and physics. Okay? Okay. I.e., it's taking some core basic ideas, some principles, inferential principles and computational ones, and control theoretic ones, and it's finding ways to put those together, build them at scale, make them reliable, et cetera, the same way a chemical engineer developed new principles. And that's not just an applied activity, by the way. Chemical engineering is not just application of chemistry and physics. Brand new mathematical principles were needed in chemical engineering, right? Same thing with electrical engineering. Impedances and circuit design principles were needed on top of classical electromagnetism. Same thing here. We are needing new theoretical mathematical principles on top of the classical statistical inferential computing things to do machine learning. All right. So in that sense, it's already, at core, it has to at least be computer science meets statistics. But really, it's a lot of other areas in applied mathematics, dynamical systems, and then there's control theory, and there's optimization has been key. I believe now economics is key. So just about every area in the information sciences which developed in the last decade, or not a century, is highly relevant, not just a little bit. But just like in chemical engineering, I think that it kind of eventually encompassed other areas like economics and public policy and so on and so forth. Here it's even going to be more than chemical engineering, obviously, because it involves human beings' data and human beings and their privacy and legal issues and social issues and all that. So, I did a little segment there in the talk on music. So it's involving the arts and culture, right? So I don't think there's a field that this thing doesn't touch. And so this thing, and again, I don't like to have definitions necessarily, but if you want to call it machine learning or data science or, but just the broader activity, bringing data together with computing, with networking, with humans and their decision making, that is the thing of the era. And so, so I believe people who are able to work between these fields are going to be really highly in need. I also have a perspective which, if you go back in the 30s and 40s, like Kolmogorov and von Neumann and Wiener and all them, they didn't think of themselves as being in one of those separate fields. They were the progenitors of all those fields, and in their mind, it was just one field. Yeah. Right? Wiener had a name for it, cybernetics. And so, I think that it's important to hearken back to that era. That's who we're looking back to. We're trying to imitate them in the modern world.
Absolutely, and I always enjoy kind of the different viewpoints that everybody can bring to the table here. That's where I think we see new ideas really explode and give us new opportunities, for the greater good of the planet. Be it in healthcare or be it in massively complex IoT systems that you mentioned at the very beginning.
Yeah, and so, just to add to that, it's multiple perspectives around the planet, around the globe. So we're often in an era where nations are looking inward nowadays, and I just want to emphasize that. To me, I'm a member of the planet in this interdisciplinary activity of machine learning, AI, whatever you want to call it. Brazil, China, Europe, etc., Africa, we're all in this together.
We are. Well, thank you again very much for this excellent presentation, all the great Q&A session interaction here. I'm afraid we have run out of time for today, so I'd like to thank one more time Michael for his great informative presentation, the insightful answers to many of your questions. And of course, really a special thanks to each one of you for taking the time today to attend and to participate. And I hope we were also able to take your mind off a little bit of, in these challenging times, take your mind off the daily news that can be a little bit depressing, and really focus on all the good that we can achieve with machine learning and AI in the future. This talk was recorded and will be available in a few days at learning.acm.org. You will find announcements on upcoming talks and other ACM activities at the same location. Also, please make sure to fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen now. And on the behalf of ACM, on behalf of Michael Jordan and myself, Michael Zeller, thank you again for joining us today, and I hope you will join us again in the near future. Stay safe, stay healthy, wash your hands frequently, and until next time. This concludes our talk for today. Thank you.